to introduce today's speaker for a special presentation, Professor Joe Kahn. This is a special seminar. It's Joe's retirement seminar. He's not retiring. He forgot to do this 10 years ago. So we've been after him for 10 years, and we finally got him to give us retirement seminar. Joe graduated from UC San Diego in 1969 and became a postdoc in Dartmouth for a couple of years. In 1972, he came here, and he's been here ever since in the GI and working in space physics. The last 10 years of his career, up to 2003, he was dean of the graduate school. He retired in 2003. After retirement, he's pursuing his two primary interests, which are his two hobbies, which are seeking inspired creativity and personal spiritual growth, and two, storm and substorm. He gave a seminar last week to the GIGSA, the pizza seminar, on topic 1. And today he's speaking on topic 2, which is storm and substorm. And this is his retirement seminar from 10 years ago.
Thank you. Today I wanted to hopefully to say something new about storm and substorm. There has been so much misconceptions floating around, and of course many well-developed observations which got mixed up by observer, experimenter, and some theorists, you name it, all kinds of things. So what I try to do is to make it very simple today, at the expense of being perhaps overly simplified, but nevertheless, I want to get a very simple point across. I just wanted to know, what does tail recognition do? And with that in mind, instead of chasing my own tail, I end up, by the way, I definitely don't follow anyone else's tail. But anyway, I found it is the solar wind magnetopulse dynamo is the main driver to power storm and substorm. And that driver, the power of that dynamo goes up or down, depending on whether the day-side reconnection dominate or tail reconnection dominates. So those are the key points. So this title is definitely for space scientists and university folks. I was hoping to attract some non-specialists, non-experts, but looks like wasn't successful. Okay. So now this is the title for the talk for people who are not really in space physics. So I call it a story. It's probably more like my story. And that was something I started in '72. When I came here, I wanted to be able to tell the story of storm and substorm before I leave here. And some of you may have heard that I was saying that even though 9 years, almost 10 years after retirement, I'm still here, still kicking, trying to understand, to have a story that I can tell about storm and substorm. And this, in the form of telling story, I divided the talk into 3 parts. Each part has some new elements in it. So let me begin. By the way, don't panic. I only have 19 slides. So now this one is for general public consumption. It's just to describe what the solar terrestrial physics playing ground looks like. This is Earth's magnetosphere, and definitely very much under influence of the sun. And the next one is also for public consumption, with a little bit detail describing what consists of in the magnetosphere. And Earth is sitting here, and then we have plasma sheet and cross-tail current and tail current, which is in the magnetopause. Then we have interplanetary magnetic field due to day-side reconnection. Day-side reconnection meaning reconnection on the day-side magnetopause. And tail reconnection wasn't drawn in this illustration, probably pretty wise, because tail reconnection is, as far as we can tell, it's kind of intermittent and patchy and come and go. And some people trying to make that to be the driver of substorm and even storm. And of course, they have a hard time even to convince anybody that it is the tail reconnection. But I'll show you what tail reconnection really is doing today. Then, of course, all important field-aligned current, which is what causes aurora brightening. And so focus on this tail current, which is also the magnetopause current, and this cross-tail current. Those are two important currents in the solar wind magnetopause dynamo. And these two currents, as you can tell, people draw it as if it's independent of each other. In fact, they are forming a loop. I call it the tail lobe current loop. I'm all in the current loop these days, including the substorm, and you'll see that current loop, because that it is common knowledge that current, if it's not flowing in a closed loop, there will be no current. Okay, so let me move on quickly to part one about the dynamo. Some people call this solar wind magnetosphere dynamo, this dynamo, that dynamo, but it's all about the same, except that after they call it, they forgot to use it. And about a few months ago, I was still looking for the driver of storm and substorm. It dawned on me. It's the closure of the dynamo current in the magnetopause, closure of that current through the cross-tail, through the plasma sheet by the cross-tail current. That's how you use this dynamo energy. Some people think, yeah, solar wind magnetosphere dynamo generate tail lobe field and stored in the tail, you name it, went on and on. And when they decide to use it, they can't reach it. They can tap that energy out through tail reconnection. So let me just say, I I somehow prefer to be oversimplified than less simplified, because that usually makes the picture clearer. So the question about where this dynamo located, it is located along the magneto tail, particularly along the magneto pulse. There's nothing new there. What's new in this day-side reconnection actually turns out to be most important for the solar wind magneto pulse dynamo, because it is the one, the day-side reconnection is responsible for producing open field lines, and open field line, when the solar wind flow across it, is what's generating the dynamo current and dynamo electric field. And tail reconnection actually has an important role to play. It reduces the open field lines. So when you have tail reconnection go full speed and start to dominate over the day-side reconnection, then your open field line will reduce. When that open field line reduces, solar wind couldn't do as much work or deliver as much power. So the dynamo power goes down. So that's one of the important part the tail reconnection is supposed to be doing. The other important part, of course, is to replenish closed field lines in the plasma sheet, which is better known than tail reconnection turn off the dynamo. People think when you get the tail reconnection going, you tap into the reserve, magnetic energy reserved in the tail lobe. And lo and behold, it was difficult. Okay. Now, comes a little detail about what day-side reconnection electric field, how does it penetrate into the closed field lines without tail reconnection? That was my problem until recently. I thought the tail reconnection is important, is responsible for allowing the reconnection electric field on open field lines to go into the closed field lines in the plasma sheet. It turns out you don't need it. If you make use of your fully utilize your dynamo property. So the key word here is that the dynamo current has to, and automatically always, closes through the cross-tail current. May not be 100%, because there are other dynamo current, such as shown by simulation, global simulation of Tom et al., myself included. It shows that the bioshock current actually closed through the plasma sheet, but that's not the dominant current loop. The dominant current loop is magneto pulse current close through the cross-tail current to form this tail lobe current loop, and the Lorentz force in the plasma sheet produced by this cross-tail current drive the earth will flow. And earth will flow, then generate electric field, cross-tail electric field. Now this is a point that Vasiliunas took a lot of pride in convincing me. I must say it's still a little bit vague in my head, but I think he's right. He said if you don't have this flow, your electric field will dissipate, will disappear. So that's in his paper. All right. So there's Sarnoff, there's Pachman, there's Vasiliunas. Now those are the three names I put a lot of trust in. Okay. So when you go through this, you know you got your daytime electric reconnection electric field now penetrate into tail closed field line in the plasma sheet without depending on tail reconnection. It's not. I'm not saying tail reconnection cannot take place. It actually must take place. The question is, what does it do? Okay. Okay. This is a dynamo tail cross section. There's actually nothing new, really, except the interpretation of. Number one, this dynamo current flows through the cross section. And number two, the dynamo electric field will penetrate into the plasma sheet on closed field lines due to the dynamo action, the Lorentz force. Okay? All right. So we back to where we were. Everybody knows this is where the dynamo region is, and this is the load region, so on and so forth. Now, tail reconnection, this is something new. I learned it from Dick Wolf. You may all have heard that Dick Wolf is fond of this entropy constraint and limitation and so on. And finally he found it, he put it to good use. So in order to reconnect open field line must be almost depleted with plasma. Otherwise, after you do the reconnection and load it with plasma, then entropy went up. Then it cannot continue moving earthward. So now I believe, based on Dick Wolf's paper, BBFs are exactly those. Empty or almost empty flux tube got reconnected and jet earthward at high speed. Now we just wanted to emphasize here that the earthward plasma flow consists of global convection, which we used to think it's the global tail reconnection and so on. Actually, this flow is very slow. 10 kilometers per second or so, at the most 20. And the BBF is a few hundred, right? Now, people tend to focus on something sexy or fast, this and that could be a disastrous consequence. So I'm back here saying, hey, it's this quasi-steady global earthward convection about 10 kilometers per second. It is that which is driving the storm and substorm. You know why? Because it has the solar wind backing it up. It's a direct connection to solar wind energy. And they say, well, what if it doesn't have enough energy to drive it. I said, well, then it's too bad. Then we lost all our storm and substorms. Because if solar wind cannot do it, nothing else will. Okay? And BBF, which we know exists, which we also know it probably produce some, what do they call it? Fine structure in the flow and so on. But it doesn't matter what you call it, because it doesn't have much to do with storm or substorm. Okay. Part 2, about storm. Driven by global earthward convection of 10 kilometers per second type in the plasma sheet, which is powered by solar wind magnetopulse dynamo, okay? And this slow flow, global flow, has two very important roles to play. One is it produces the global non-uniform anisotropic overconductance, which I suffer a lot by not knowing the existence of overconductance. When the activity is low, you have this non-uniform conductance in the ionosphere at the lower level. When the flow builds up, that conductance enhances, whether you have aurora activity or not. But that's another story. Anyway, it's very important because it's non-uniform and it's anisotropic. And then we come to the most, maybe at this time, still quite confusing